On the morning of September 15th, 2017, a spacecraft the size of a school bus made its final approach toward Saturn, and instead of pulling away the way it always had before, it kept going, straight down into the planet's atmosphere. Its small thrusters fought to keep its antenna pointed at Earth for as long as physically possible, fighting against the increasing resistance of Saturn's thickening gases, sending back real, live data the entire time. Then, in a matter of seconds, the signal simply stopped. Not because the mission ended cleanly, on schedule, in some tidy planned shutdown. It stopped because the spacecraft itself had been torn apart, burned up like a meteor in the sky of a planet it had spent 13 years quietly studying. And in those final seconds, as its instruments kept sampling the thickening atmosphere around it right up until the connection was lost, it sent home a piece of data that scientists are even now, years later, still struggling to fully explain. Strong evidence that the magnetic field generated deep inside Saturn is aligned with its spin axis in a way that, according to a well-established piece of physics called Cowling's theorem, shouldn't be physically possible for a magnetic field to sustain itself over any meaningful stretch of time. This is the story of Cassini's final plunge into Saturn, what its instruments actually recorded in those last minutes and seconds before the signal went silent, and why one particular finding from that mission remains one of the more genuinely puzzling open questions in modern planetary science. To understand why those final moments mattered so much, and why the mission was designed to end that way at all, you have to go back to how Cassini got to Saturn in the first place, and to a discovery made years earlier that made a deliberate, controlled destruction the only responsible way to end the mission. Cassini launched on October 15, 1997, a joint mission between NASA, the European Space Agency, and the Italian Space Agency, carrying with it a smaller probe called Huygens, built specifically to descend through the thick, orange atmosphere of Saturn's largest moon, Titan. After a journey lasting nearly 7 years, Cassini entered orbit around Saturn on June 30, 2004, becoming the first spacecraft in history to orbit the ringed planet directly, rather than simply flying past it the way earlier missions, including both Voyager spacecraft, had done decades earlier. In January of 2005, the Huygens probe separated from Cassini and descended through Titan's atmosphere, landing successfully on its surface and transmitting data for over an hour afterward, becoming the first, and to this day, still the only, spacecraft ever to land on a world in the outer solar system. What followed was one of the most scientifically productive planetary missions in the history of space exploration. Over the following 13 years, Cassini's original 4-year primary mission was extended twice, and during that extended time, it made discoveries that fundamentally reshaped scientific understanding of the Saturn system. It found strong evidence of a vast global liquid water ocean hidden beneath the icy surface of Saturn's small moon Enceladus, along with active geysers erupting from that moon's south pole, spraying water vapor and ice particles directly out into space, some of which fell back down to coat the moon's surface, and some of which escaped entirely to help form one of Saturn's outer rings. It discovered liquid methane and ethane seas on the surface of Titan, the only other place in our solar system, besides Earth, known to have stable liquid on its surface, even though on Titan, that liquid is frigid, hydrocarbon-based rather than water. It photographed Saturn's atmosphere in extraordinary detail, including the massive, persistent, hexagonal storm pattern swirling around the planet's north pole, a genuinely strange, still not fully understood atmospheric feature, roughly wide enough to fit 4 Earths inside it. By 2017, after 13 years in orbit, Cassini was running low on the rocket fuel needed to maintain and adjust its orbit. That created a serious, sobering problem for the mission team, one with real ethical and scientific weight behind it. An uncontrolled spacecraft, left adrift on its own once its fuel ran out entirely, could eventually, over years or decades, end up on a collision course with one of Saturn's icy moons, potentially Enceladus or Titan, both of which scientists consider genuinely promising candidates in the ongoing search for life beyond Earth. Cassini, having spent 13 years exposed to the vacuum of space, could not be guaranteed free of any hardy, dormant microorganisms that might have survived from its original construction on Earth. Crashing an uncontrolled, potentially contaminated spacecraft onto a world capable of hosting a habitable, subsurface ocean, one scientist's hope to study very carefully for genuine signs of biology in future missions, represented an unacceptable risk under NASA's own planetary protection guidelines, established specifically to prevent exactly this kind of accidental contamination. The solution the mission team settled on became known as the grand finale, and it turned Cassini's necessary, unavoidable end into one of the most scientifically valuable phases of its entire 13-year mission. Rather than simply allowing the spacecraft to drift once its fuel ran low, engineers deliberately placed Cassini on a carefully calculated impact course, one that would ultimately send it plunging directly into Saturn itself, a planet with no solid surface to protect, and therefore no risk of biological contamination to worry about at all. Getting there involved a series of 22 increasingly daring orbits, beginning in April of 2017 and continuing over roughly 5 months, each one threading Cassini directly through the narrow, roughly 1,200-mile wide gap separating Saturn's cloud tops from the inner edge of its rings, a region no spacecraft had ever dared fly through before, precisely because the risk of colliding with unseen ring particles had always been considered too dangerous to attempt during the earlier, primary phase of the mission, when protecting the spacecraft's long-term survival still mattered. With Cassini's fuel running out regardless, that calculus changed entirely. As NASA's own mission description put it plainly, at times the spacecraft skirted the very inner edge of the rings, and at other times it skimmed the outer edges of Saturn's atmosphere, testing limits the mission's original designers had never intended it to approach. It was, in the words of NASA's own materials describing the phase, the kind of bold adventure that could only be undertaken at the very end of a mission, once there was genuinely nothing left to lose by taking risks that would have been unthinkable at any earlier stage. Those 22 close orbits turned out to be extraordinarily scientifically productive, providing an entirely new, previously unreachable vantage point on regions of the Saturn system that decades of more cautious observation had never been able to directly sample. And then, on September 15, 2017, having completed its final close approach, Cassini made its last dive, deliberately, directly into Saturn's atmosphere itself, sending back real-time data for as long as its small attitude control thrusters could continue fighting against the planet's increasingly thick atmosphere to keep its antenna pointed steadily back toward Earth. Once atmospheric resistance finally overwhelmed those thrusters' ability to maintain that orientation, the signal was lost, and shortly after, the spacecraft itself burned up and disintegrated, essentially the way a meteor does, scattering harmlessly into the deep atmosphere of the very planet it had spent 13 years studying. According to NASA's own published mission materials, even those final seconds of transmitted data carried unique, valuable information about Saturn's atmospheric composition, gathered by Cassini's ion and neutral mass spectrometer, an instrument specifically designed to directly sample and analyze the gases immediately surrounding the spacecraft as it descended. That instrument continued measuring the changing composition of Saturn's upper atmosphere right up until the very end, providing scientists with the first, and to date only, direct, in situ sampling of Saturn's atmosphere ever obtained by any spacecraft, a genuinely unique dataset that simply could not have been gathered any other way. Beyond that final atmospheric sampling, the broader grand finale campaign, spanning all 22 of those daring close orbits, produced a substantial body of new findings, published across a special issue of the journal Science in October of 2018, alongside a companion set of papers and geophysical research letters. Several of these findings genuinely reshaped scientific understanding of the Saturn system, while at least one, involving the planet's magnetic field, opened up a puzzle researchers are still actively working to resolve today. One of the more immediately striking discoveries involved Saturn's rings themselves, and specifically material raining down out of them directly into the planet's atmosphere. Scientists had actually proposed, based on indirect remote observations dating back roughly 40 years, that Saturn's powerful magnetic field was likely responsible for funneling charged ice particles and dust from the rings down toward the planet's middle latitudes, a process sometimes informally referred to as ring rain. The grand finale orbits finally provided direct, first-hand confirmation of this process, and revealed it to be considerably more complex, and in some ways more surprising than the earlier indirect models had suggested. According to findings published through the Johns Hopkins University Applied Physics Laboratory, Cassini's instruments detected fast-moving molecules and exceptionally small particles, some measuring less than 2 nanometers across, streaming directly along the plane of the rings and down into Saturn's atmosphere, a discovery the researchers themselves described in their own published statement as genuinely startling, since it revealed an entirely different transport mechanism than the one scientists had spent 4 decades assuming was responsible for moving material from the rings down into the planet. Related research, combining the grand finale's direct atmospheric sampling with detailed gravity measurements of the rings themselves, allowed scientists to make considerably more precise estimates of the rings' total mass, and by extension, their likely age, a question that had remained surprisingly unresolved despite Saturn's rings being one of the most recognizable, most extensively photographed features in the entire solar system. That mass estimate, combined with measurements of the rate at which ring material continues raining down into the planet's atmosphere, indicated that Saturn's rings are considerably younger than the planet itself, likely having formed sometime within roughly the last few hundred million years, an extraordinarily recent event by the standards of a solar system that's existed for over 4.5 billion years, and evidence that the rings themselves are likely to continue dissipating and eventually disappearing entirely over a timescale of a few 100 million years into the future, as material continues steadily raining down out of them and into the planet below. The grand finale orbits also revealed the existence of an entirely new radiation belt, one nobody had previously detected, sitting within the gap between Saturn's D ring, its innermost ring, and the planet's own atmosphere. According to the research team responsible for identifying it, this newly discovered belt appears to be sustained not by the kind of charged particle acceleration processes typically responsible for radiation belts around other planets, but instead by the radioactive decay of free neutrons, a genuinely unusual mechanism for maintaining a planetary radiation belt, and one that had never previously been directly observed anywhere else in the solar system. Cassini's instruments also detected clear evidence of electric currents flowing directly between Saturn's innermost rings and the planet's own atmosphere, another entirely new finding made possible only by the extraordinarily close proximity these final orbits allowed, threading directly through the narrow gap where that electrical connection could finally be measured firsthand, rather than inferred indirectly from a greater distance, the way earlier observations had been forced to rely on. Perhaps the most immediately practical of the grand finale's findings involved something scientists had, for years, referred to informally as Saturn's energy crisis, a long-standing puzzle involving the planet's overall thermal balance, essentially a mismatch between how much energy Saturn's upper atmosphere appeared to be radiating away and how much energy models suggested it should actually have available to radiate based on the combination of heat retained from its formation and the relatively small amount of additional heat it receives from the distant sun. Nearly 3 years after the grand finale concluded, researchers analyzing the full combined data set finally resolved the particular mismatch, publishing findings that helped explain how Saturn's overall energy budget actually balances out once additional details about its atmospheric structure and internal heat distribution, gathered specifically during those final close orbits, were properly accounted for. All of these findings, remarkable as each one is on its own, represent puzzles that Cassini's final data ultimately helped solve, examples of genuine scientific closure brought about specifically by the spacecraft's willingness to take risks during its final months that would have been unthinkable earlier in the mission. But one particular finding from those same final orbits remains stubbornly, genuinely unresolved, and it's arguably the most conceptually puzzling result to come out of the entire grand finale campaign. Here's the background necessary to understand why this specific finding caused such a stir among planetary physicists. Every planet with a magnetic field, including Earth, generates that field through a process called a dynamo, driven by the movement of electrically conductive material, molten metal in Earth's case, deep within the planet's interior. A well-established piece of theoretical physics called Cowling's theorem, developed decades ago through careful mathematical analysis of how these dynamo processes work, establishes that a magnetic field generated by a perfectly symmetric process, one that's precisely aligned with a planet's rotational axis in every respect, cannot actually sustain itself indefinitely. The theorem demonstrates that some degree of asymmetry, some meaningful tilt or irregularity between a planet's magnetic field and its rotational axis, is mathematically required to keep the underlying dynamo process actively generating that field over any extended stretch of time. Without that asymmetry, the theorem shows, the field should gradually decay and eventually disappear entirely, rather than persisting for billions of years the way we actually observe planetary magnetic fields doing. Earth's own magnetic field reflects exactly this kind of expected asymmetry. Our planet's magnetic poles don't align perfectly with its geographic rotational poles. They sit measurably offset from them, currently by roughly 10 degrees, a real physically meaningful tilt that helps satisfy the conditions Cowling's theorem describes as necessary for a magnetic field to remain self-sustaining over geological timescales. Saturn's magnetic field doesn't behave that way at all, and scientists have actually known this was strange since NASA's Pioneer 11 spacecraft first flew past the planet back in 1979. Saturn's internal magnetic field appears to be almost perfectly symmetric relative to its spin axis, tilted by an angle so small that, for decades, it remained difficult to even measure with any real confidence using the kind of remote, distant observations available before Cassini's grand finale gave scientists the chance to measure it directly, up close, for the first time. As one of the papers published in that October 2018 special issue of Science put it directly, Saturn's internal magnetic field is puzzling, specifically because of this unusually high degree of symmetry relative to its spin axis, a genuinely established observation dating back decades, one that Cassini's final, closest ever measurements were specifically designed to help pin down with far greater precision than had ever previously been possible. Cassini's magnetometer during those final grand finale orbits made detailed in situ measurements of Saturn's magnetic field from distances of only a few thousand kilometers above the planet's cloud tops, closer than any previous spacecraft had ever measured that field directly, The resulting data, analyzed by a research team led by Michelle Doherty, confirmed with considerably greater precision than any earlier observation that Saturn's magnetic field really does appear to be tilted by an angle so small it remains, even now, difficult to measure with full confidence. An alignment that sits in genuine, direct tension with what Cowling's theorem suggests should be physically necessary for that field to have persisted as long as it clearly has. This isn't a minor academic curiosity easily brushed aside. It creates a genuine practical scientific problem that extends well beyond simply being conceptually puzzling. Because Saturn's magnetic field is tilted by such an extraordinarily small angle, scientists have found it exceptionally difficult to use that field to determine something that might otherwise seem straightforward. Exactly how fast Saturn's deep interior actually rotates. For most planets, including Jupiter, the magnetic field itself, generated deep within the planet's interior, and typically offset at a measurable angle from the rotational axis, functions almost like a clock hand, allowing astronomers to precisely track the planet's true interior rotation period by carefully monitoring how that offset field sweeps around as the planet spins. Because Saturn's field is so close to perfectly symmetric, that natural clock essentially doesn't exist in any usable form, and determining Saturn's true interior rotation rate has remained a genuinely difficult, only partially resolved problem, even after Cassini's grand finale provided the most detailed magnetic field measurements ever obtained for the planet. The research team analyzing Cassini's final magnetometer data proposed that the explanation likely involves what they described as a complex, multi-layer dynamo process occurring deep within Saturn's interior, potentially involving several distinct layers at different depths, each contributing to the overall magnetic field in ways that could, in principle, help mask or average out the kind of asymmetry Cowling's theorem suggests should otherwise be directly observable from outside the planet. That's a genuinely plausible theoretical framework, and it represents real, serious scientific progress toward eventually resolving the puzzle. But it remains even today a proposed explanation rather than a fully confirmed, settled one. And scientists studying Saturn's interior continue working to develop and test more detailed models capable of fully accounting for exactly how the planet's deep interior manages to sustain a magnetic field this remarkably well aligned with its spin axis, in apparent tension with a well-established piece of theoretical physics that is otherwise held up reliably across every other magnetized planet in the solar system. It's worth being precise and appropriately careful about what this puzzle does and doesn't actually represent, since that distinction matters considerably more than any dramatic framing built around it. This isn't evidence of anything supernatural, and it doesn't suggest Cowling's theorem itself is somehow wrong. The theorem remains a well-established, mathematically rigorous piece of magnetohydrodynamics, confirmed repeatedly across decades of study involving Earth's own magnetic field and those of other planets. What Saturn's unusually symmetric field genuinely represents is a real, still open question about the specific, detailed internal structure and dynamics operating deep within Saturn's interior, one that requires a more sophisticated dynamo model than the relatively simpler frameworks that adequately explain magnetic field generation on planets like Earth and Jupiter. Solving it fully will likely require additional data, potentially gathered by some future mission capable of measuring Saturn's magnetic field with even greater precision than Cassini's final, closest ever orbits managed to achieve, or through increasingly sophisticated computer modeling capable of simulating exactly the kind of complex, multi-layered dynamo behavior researchers currently suspect is responsible for the effect. There's something genuinely fitting about the fact that Cassini's mission, having spent 13 years methodically answering question after question about the Saturn system, ended by handing scientists one of its most enduring, still partially unresolved puzzles, gathered specifically during the final, riskiest, most scientifically ambitious phase of its entire operational life. The spacecraft's builders and mission planners never set out specifically hoping to leave behind an unsolved mystery. The grand finale's design was driven primarily by the practical, ethical necessity of safely disposing of a spacecraft that could no longer be trusted to maintain its own orbit indefinitely. And yet, in the process of executing that necessary, carefully planned final act, threading 22 increasingly bold orbits through a region of space no spacecraft had ever dared enter before, Cassini managed to gather exactly the kind of close, detailed, previously unobtainable data needed to both resolve several long-standing scientific puzzles about Saturn and simultaneously reveal a new one involving the planet's deep, hidden interior that researchers are still actively working through today. Cassini's own final seconds of transmitted data, gathered by its mass spectrometer as the spacecraft's small thrusters fought a losing battle against Saturn's thickening atmosphere, represent the literal last measurements that instrument and that entire 13-year mission ever managed to send home. They arrived not because anything went wrong, but because everything, in a very real sense, went exactly as carefully planned, a deliberate, controlled ending chosen specifically to protect the possibility of future discoveries at Enceladus and Titan, worlds Cassini itself had first identified as genuinely promising candidates in the broader search for life beyond Earth. In sacrificing itself to protect that possibility, Cassini managed, in its very last moments, to hand scientists one more genuine mystery about the planet it had spent 13 years quietly, patiently getting to know, a puzzle about magnetism and hidden internal structure that researchers are still, years later, carefully working to fully understand. If you want to follow how scientists continue working through that puzzle, and what future missions might eventually reveal about what's really happening deep inside Saturn, that story is still being actively researched today. Subscribe if you'd like to keep following where it goes.